Hi, my name is Scott Simpson, and today we'll be talking about normalization. So normalization is a process that you have to do when you're looking at a wave function and it's unnormalized, meaning if you were to take the probability, basically if you were to look at complex conjugate of your wave function and you were trying to get the probability for this function to be normalized, if you're integrating over all possible space, it has to be equal to 1. So, for example, if we go from negative infinity to infinity across all space, it should equal 1. So for normalization, the probability of the particle with the wave function psi has to be equal to 1 over all space. Of a particle with wave function psi has to be equal to 1 over all space. And most of the time for this to happen, you generally have a function and you have what's called a normalization constant. You apply this normalization constant to your wave function, and then when you integrate, you should get 1. So for this to happen, a scaling factor, that normalization constant, sometimes called or normalization constant, or it's just called normalization. A normalization constant must be applied to the original function. Must be applied. The original function. So we're going to show this normalization constant just with the letter A. So your wave function psi should actually become A times psi. So let's look at an example of this. In this example, we have a non-normalized wave function. The non-normalized wave function of a system is, we have psi x is equal to sine 3 pi x over 4. And what we want to do in the example is determine the normalized wave function if the limits are from 0 to 1. Okay. So if we have a normalized wave function, we know over the limits it has to be equal to 1. So what we're going to do is we're going to introduce a new term A, and A is the normalization constant. So we have A times psi x. We have to take the complex conjugate of that. If you're not sure what the complex conjugate is, there will be another video on it. Just check and look for it. Basically, wherever you have an imaginary I, it becomes a negative I in that case. Times A, that same wave function, beta. Okay, and we've specified our limits. We said our limits are from 0 to 1. Now, we know if we do this, the result should be 1. The reason is if we're integrating across all possible spots that the particle can exist, it has to be equal to 1, meaning it has to be somewhere in that range. Okay, so let's start doing some mathematical manipulation. We'll solve in for our size. We can pull our A constants out. 1 sine, what did we do, 3 pi over 4x times sine 3 pi over 4x dx. That becomes a square, so we've got a squared from 0 to 1 sine squared 3 pi over 4x dx. Now, that looks a little bit tricky. I personally don't want to solve this. What I would do is look up an integration table, and you can find the results of a lot of these sines and cosine functions that you'll encounter a lot in physical chemistry. So, we can look up a reference table. From reference table of integrals. We got sine squared of bx is equal to x over 2 minus 1 over 4b sine 2bx. Okay, so if we look back at our original function, it follows the same form. We know what b is in this case. b is going to be equal to 3 pi over 4. So now we can use this integral to solve for that guy. Zip that around. So we still keep our a squared. We have our integration done. We have x over 2 minus 1 over 4 times b. In this case, b is 3 pi over 4, so we would have 3 pi like that. Then we get sine times 2 our b again, so 3 pi over 4x. We keep our integration limits from 0 to 1. Let's simplify this a little bit further. A squared x squared minus 1 over 3 pi sine 6 pi over 4 times x from 0 to 1. Okay, let's sub in our integration limits and let's see what the result is. So we still keep our a squared. We'll deal with that in a moment. We got from 1 to 0, so we got 1/2 minus 1 3 pi sine 6 pi over 4 minus 0 over 2, so we get 0 minus, actually a plus technically, because there's a negative sign here. We'll get 1 over 3 pi sine of 0. Of course, sine of 0 is 0, so that term's going to drop out. So in reality, we're just left with these first two terms. Sine of 6 pi over 4 is actually -1, so this becomes a -1 value. And what we get is a squared plus 1 over 3 pi. Okay. Now what we can do is we can look at this value. We know what this whole term here has to be. It has to be equal to 1. Let's manipulate this and solve for a squared. Numerically, if you determine this, what this becomes is a squared times 0.6061. This is just a collection of constants is equal to 1. Now what we're going to do is we're going to move that a squared over, and we're going to try to solve for it. So we can do that. So we're talking about this portion here. We're just going to move that a squared over, or excuse me, we're going to move that number over. So we get a squared is equal to 1 divided by 0.6061. Then we just got to square both sides, you get the square root of 1 over 0.6061. If you manipulate that mathematically, what you get is 1.2844. Okay, so now we have our normalization constant. We have to conglomerate that with our original wave function. So our original wave function was sine 3 pi over 4 times x. We have to tack on that normalization constant, so 1.2844 times this guy. That is going to be our normalized wave function. So this is what we would use if we were looking for other properties, expectation values, probabilities of finding this particle in a location of 0 to 1. Okay, so if you're unsure of where to go from here, there are additional videos that will be posted to show you how to manipulate this. This is a very important topic in terms of quantum mechanics. You should know how to normalize a wave function, any wave function that you come across. If you have any questions, please feel free to email me or leave a comment below. Thank you for your time.